The word percentage is made up of two words, per and cent, where per means divided by and cent means 100. If 9 boxes are considered out of 100 boxes, then the percentage will be 9%. And if all 100 boxes are considered out of 100 boxes, then total percentage will be 100%, which will be 100 by 100, which is equal to 1. If the number of boxes is not 100, we can still calculate percentage. If 6 boxes are considered out of 50 boxes, then let X% be the total percentage, which can be calculated as shown on screen. This process is same as the following process. Divide the portion considered by total number of boxes, then multiply by 100%, which is equal to 1. This way we can calculate percentage, which is same as previous percentage. So we know that percentage is equal to portion divided by total. We can multiply by total number of boxes on both sides of the equation to get this. Now let's talk about growth. In the beginning we have growth is equal to original. At time is equal to 1 unit. Something has increased. I am gonna call that increment. So growth after 1 unit will be original plus increment. Increment can be considered as part of the original. I am using the words part and portion as synonyms of each other. So growth is equal to original plus portion. After 2 unit time, increment will be twice the portion. So growth will be original plus 2 times portion. Now if we continue this process, then after t time, increment will be t times portion and growth will be original plus t times portion. Here I used portion increased each second to match their units. We can substitute the value of portion and can take out original out of the bracket. Percentage increased each second is rate of increment. So we had this equation. We can replace one box with $1. In terms of money, growth is called amount, original is called principal, rate of increment is called rate of interest, and T is called time. This second term is called simple interest. Let's write this formula in its short form. This is what each letter denotes. This line represents the time small t. The growth after small t time will be this much. What if we divide this time into intervals? The growth after t1 time will be this much. Let's treat this point as initial time for the remaining time. At this point, amount after t1 time will become our new principal. From this point, the growth after remaining time t2 will be this much. Let's substitute the value of p new to get this expression. Similarly, if the interval is divided into 3 parts, then the growth after small t time will be this much. If we divide the time in n unequal intervals, then this will be the total growth after small t time. Now let's derive the formula for equal intervals. If small t is divided into n equal intervals, then small t will be n times capital T and growth will be this much. We have this formula to calculate simple growth and this formula to calculate compounded growth. And using this relation small t is equal to n capital T, we can calculate compounded growth in three different ways. And this is what each term means in these formulas. This is what these term means in other words. Let's compare simple and compound interest with this example. For compound interest, we need to tell either time period or frequency apart from the terms used in simple interest. As you can see, compounding makes something grow faster. Let's take time period equal to half year. You can see that as time period becomes smaller and smaller, the growth becomes bigger and bigger. Let's see a special case of this formula for total time equal to 1 unit. In this case, n becomes the inverse of time period, which means n is the frequency of compounding. This is Jacob Bernoulli. In 1683, he was studying a question about compound interest. You can see the question on the screen. Let's convert these sentences into symbols. That question is now written in its compact form. Let's substitute these values in this formula and simplify. We get this expression. Now let's consider the question what if n increases? For n equal to 1, the growth is 2. For n equal to 2, the growth is 2.25. For n equal to 5, the growth is 2.488. And this is growth for other values of n. For n equal to 0 0.1 million, the growth is 2.7182. As you can see, AC increases as n increases. N increases means frequency increases. It's natural to ask what if n tends to infinity. In other words, what if frequency tends to infinity. But what does frequency tends to infinity mean? Frequency tending to infinity means time period tending to zero, which means continuity. In this case, continuity of compounding. As n tends to infinity, the growth tends to a constant, and this constant is known as Euler's number and is denoted by small e. Therefore, small e is equal to this expression, which we get when in compound interest p equal to 1, r equal to 100% for small t equal to 1, and the compounding happens continuously. Therefore, small e is a constant we get when something start with a unit and which produces a thing equal to itself per unit time for 1 unit time. And as n equal to 1 over capital T, we have this other expression for smaller n. What if initial value, rate of growth and total time were different? For that we will get the following expression. As p does not depend on small n, we can take it out of the limit. Let Rt over small n be capital N. We can treat R and T as arbitrary constants, which means if we divide infinity by R and T, we don't get any indeterminate form, which means 1 over capital N tends to infinity, which means capital N tends to 0. When something tends to infinity, treat it as frequency, and when something tends to zero, treat it as time period. Recall that the expression inside the bracket is small e by definition. So continuous growth with initial value capital P, growth rate capital R, and total time small t is P times e to the power capital R times small t. It's useful to remember that AC equals this limit, and anytime we find this kind of limit, we can simply write P e to the power RT. There are two types of growth, discrete and continuous. For example, trees grow little by little, not suddenly. Many things in nature grow continuously too. To understand and calculate these continuous changes, we need a special way of thinking. On the other hand, many things like possible outcomes of coin tosses is discrete. 100% discrete growth has the same effect as 69.3% continuous growth. The continuous growth requires a smaller rate because of compounding. Remember that by convention I am using small n for discrete values and small x for continuous values. One question arises naturally whether we should use continuous growth or discrete growth. And the answer is it depends on the scenario. If growth happens in a human-made system, discrete growth works better. And if growth occurs in a natural system, continuous growth is better. Coin tossing is a great example of discrete growth. If we flip one coin, we may have either head or tail, which is two possibilities. If we flip two coins, we have four possibilities. If we flip three coins, we have eight possibilities. And for n flips, we have 2 to the power n number of possibilities. Total number of possible outcomes of coin flips grows exponentially but discretely, which depends on number of coins. If we plot a graph between number of coins and total number of possibilities of outcome, it looks like this. We can model discrete growth by continuous growth, but this is similar to saying a family has 2.3 kids on average. That's why we use discrete growth for tossing a coin. If the growth rate of an exponential function is negative, we call it exponential decay, which can be continuous or discrete. Radioactive decay is a great example of continuous growth with negative rate. When something like radioactive material breaks down, we talk about its half-life, how long it takes for half of it to disappear. For example, carbon 14 takes 5730 years to lose half of itself. We can write a simple equation to show this. If we wait 5730 years, we accept 50% of the carbon remaining. If we double that and wait 11,460 years, we expect 25% of the carbon remaining. But here's the thing, the material doesn't actually break down in sudden jumps. It doesn't wait for a specific time to pass before changing. It's changing all the time. We use simple equations to help us understand, but in reality, the change is happening continuously. The radioactive material is changing every instant. We use half as the base because we humans want to count the number of halvings, like decaying into half, decaying into a quarter, decaying into an eighth, etc. To really understand this continuous change, we can use a special math formula that shows the change happening instantly, not just in big jumps. We can find the continuous decay rate by converting the discrete growth into a continuous pattern shown on the screen. This helps us calculate the change at any moment, not just after a certain amount of time has passed. In real life, scientists don't wait for half of the material to disappear to figure out its half-life. They measure the change over a reasonable amount of time, like a year, and then use math to calculate the half-life. By continuous growth, we can calculate the growth in instant by instant basis. None of this. Wait until it decays by 50% so we humans can count it easily. Nonsense. Carbon 12 isotope of atom is abundant on Earth. It makes up about 98.9% of all carbon found in nature. Nitrogen 14 converts in carbon 14 through a process called cosmic ray spallation. This occurs when cosmic rays interact with nitrogen 14 in Earth's atmosphere, causing a neutron to be ejected and converting nitrogen 14 into carbon 14. C14 is a radioactive element which decays over time. Meanwhile, C12 remains fixed because it's not radioactive. By knowing the ratio of C12 to C14, we can find the age of fossils or rocks accurately up to 60,000 years. This is the principle behind radiocarbon dating, which is useful for biologists, archaeologists, geologists, and historians. Population growth model depends on the animal. For example, population growth of bacteria is modeled by continuous growth because so many bacteria are in different stages of growth. On the other hand, population growth of rabbits is discrete. Let's try to raise e to some imaginary number. We can substitute ix in place of rt to get this and write the number inside in polar form. After simplifying, we find that r to the power n equals 1 as n tends to infinity. Now we can apply de Moivre's theorem, which is available on this channel. If theta is measured in radians, then theta equal to L upon R, and for unit circle, theta equal to L. As n tends to infinity, x by n equals L, but L equals theta, so x by n equals theta. Substitute theta in above equation and simplify. Since there is no n left, we can remove the limit and replace x by theta, which is different from the theta we used earlier. This is Euler's formula, which says that any complex number on unit circle making an angle theta can be expressed like this. Let's find the complex conjugate of e to the I theta. Minus sin theta equals sin minus theta, and cos theta equals cos minus theta. Hence complex conjugate of e raised to I theta is e raised to the power minus I theta. Here is how you can write e as sum of infinite series. Its prerequisite is binomial theorem. This is series expansion of e to the x. Here is why e is irrational. On the contrary, assume that e is rational. Let's multiply both sides of this equation by q factorial. Set of integers is closed under addition, subtraction and multiplication. So this is an integer. This is also an integer. Hence this must be an integer. I will label it a. Remember, a must be integer. Let's simplify a. A is less than this number. Inside the brackets is a geometric series. Whose solution is this. So a lies between 0 and 1, which means a can't be an integer. I think Galileo want to say something about this. So our assumption that e is rational is wrong. Therefore, e must be irrational. Here is the derivative of e to the x.